We're now going to look at rational functions. And we're going to look at some algebra and some calculus and some graphing. Some of this should be review, but I will go ahead and I'm just going to work through some problems out of the book. And hopefully this will help you as you attempt to solve your homework problems. First of all, a rational function, to put it simply, means it's going to be an expression that's like a fraction. Matter of fact, the very first, I'll just write down the first problem I'm going to look at. X plus 4 over x minus 2. Now, as we go through these problems, one of the ultimate goals, let me write down this is just me sort of giving my impression of what's going on with each problem. The ultimate goal as we work the rational functions, they want you to be able to come up with a graph, or at least a rough sketch of a graph. Sometimes this isn't too bad, but sometimes it takes a fair amount of work and you have to even plot some points and stuff. And then they also let me just call this algebra topics. I'm just sort of actually making this up. And by that, I mean they're going to ask you about asymptotes. They're going to ask you about intercepts. These are the kinds of things that we derive from just doing algebra on our rational expression. But then there are things we also learn, or they ask us, that involve calculus, like maximums and minimums. When is the graph increasing, decreasing? Points of inflection, I could write concavity. So there's a lot of stuff going on. So what's going to happen is normally you take an expression and you do your algebra stuff first. You try and learn what you can. And part of what you learn will help you with your graph. And then you go, you do some calculus on the expression, learn what you can. And some of that will help you with the graph. And then toward the end, a lot of times is when you actually try and create the graph. But they will ask you for specific information about asymptotes, intercepts, maxes or mins, regions where it increases or decreases, points of inflection, all that kind of stuff. So that's sort of the big picture. So let's start in the book, and in your homework, they're going to start with like algebra topics. And the first one's asymptotes. And real quick, this should be review. In my mind, it really breaks up into two asymptotes, vertical and then horizontal or oblique. Sometimes people call them slant asymptotes. Obviously, a vertical asymptote means up and down, horizontal, left and right. Oblique or slant means it's a straight line, but it's at an angle. So our job is to look at our function, our expression, see if there are any vertical asymptotes, what they are, see if there are any horizontal or oblique asymptotes, and see what they are. So how do we go about that? Well, vertical asymptotes, we've gone over this before. It's all about the denominator. And that's all. Well, it's going to be one little caveat, you'll see in a minute, but it's 98% all about the denominator. Horizontal and oblique, we'll do some examples later on. I can't sort of summarize it in just one word. So let's do this. Let's look at some problems. And the first thing it has to do is to find vertical asymptotes. So let's go back to this one right here. Vertical asymptote, if you recall, is you look at your denominator and you decide what value of x would cause the denominator to be 0. Because once again, an asymptote will be on a graph. Asymptotes are designated by sort of dashed lines. And the basic idea is when you have a graph, your graph cannot touch or cross an asymptote. Now, on some graphs, it will cross it here in the middle of the graph. But when you get to the edges of the graph, your lines, your function should never cross or touch an asymptote. So here's a vertical asymptote. Here's a horizontal. So if you have something like this, maybe your graph will like have two parts. Maybe it looks something like this, where you can see I'm not crossing or touching the asymptotes, although as it gets further away, my function of my graph sort of tracks or goes right next to the asymptotes. An example of a slant asymptote or an oblique asymptote is maybe something like this. Maybe I have a vertical and maybe I have an oblique asymptote, and maybe once again, maybe my graph is in two parts. Once again, my graph or my function never crosses or touches an asymptote, but it gets right next to it and sort of tracks it. So these are the kinds of things now we're going to start looking at. So we need to figure out all the information for these asymptotes, figure out what they are, where they are. So once again, let's look at vertical first. Vertical's probably the easiest thing you're going to do. You simply look at the denominator, and 98% of the time you're done. Although there is one quick thing you have to check, which every once in a while they'll throw you a curveball. I'll get to that in a minute. You ask yourself, what's the value of x that would cause the denominator to be 0? Because in a sense, what that means is, if I look at this, x cannot ever equal 2. Why? Because if x equals 2, then the whole denominator is 0, and I can never divide by 0. So just common sense says, hey, x better not ever be equal to 2. What follows is, therefore, the equation for the asymptote, when we're going to draw it, what we're going to draw is the line x equal 2. So we say the asymptote is x equals 2, which really means if we were to start graphing it, we would go x equals 2 is a vertical line, and you draw a dashed line, and there's the asymptote x equals 2. The dashed line means it's an asymptote. So yeah, it's like when you give the answer, if they want the equation of the asymptote, you say x equals 2. Although really what we're saying in practical sense is the function can never equal 2. if I were to graph this function, it can never touch or cross this dashed line. Which makes sense, because what happens if it crosses or touches the line? That means x equals 2. What happens when x equals 2? Then you have 0 in the bottom, and then this whole thing blows up, and then you get real problems. Now, let me give you the one caveat, and I think there's one problem we're going to look at where it comes into effect. The only time all this I've said is not true is occasionally when you look at your denominator, we call this sort of a factor, x minus 2. I could just make up an example. Say this was your function, x plus 4 times x minus 2 over x minus 2. Normally, someone might come in here and say, well, if I'm looking for the vertical asymptotes, all I look at is the denominator. And I would say the vertical asymptote is x equals 2. And that's true about 98% of the time. The one time where it's not true are those special cases where if they have the same factor in the top and the bottom, in other words, I was looking at this to figure out my vertical asymptote, but I've got the same thing in the top. If this happens, then this sort of cancels out the vertical asymptote. If you remember in algebra, what you would have instead of a vertical asymptote, you have a hole at x equals 2. I can go into this. So this is the one. So anytime you're finding vertical asymptotes of the denominator, 98% of the time it's correct, but just look up at the top and make sure you don't have the exact same factor in the top. This one we don't, obviously, right? So the asymptote is x equals 2. A couple more quick examples now that I've tried to beat that horse. How about f of x equals 5x over x squared minus 25. Rational expression. It's interesting, I got an x up here, but you know what? X in the numerator has no impact on vertical asymptotes. All I care about is right at the denominator. Now, the only way I'm going to actually be able to figure out the vertical asymptotes in this case is I have to factor. So if possible, you always have to factor the denominator. This is a difference of squares. So if I look at the denominator, I say, what are the values of x that would cause the denominator to be 0? Well, this first parenthesis if x is minus 5, the denominator is 0, and the second parenthesis if x is 5, it's 0. So therefore, x cannot equal negative 5 and 5. And therefore, the equations are my asymptotes. There are two of them, x equals 5, negative 5 and x equals 5. So if we were just to draw the asymptotes, all right, not too hard. Just had to factor here. And let's do a couple more. About x plus 3 over x cubed minus x. So we're asked to find the vertical asymptotes. Once again, I'm looking at the denominator. Possible I didn't factor. Matter of fact, I'm just going to, well, I'll go and write it. Usually I ignore it, but I can factor out an x. And then I realize x squared minus 1 is a difference of squares, so I can factor some more. So it looks like I've got 3 factors in the denominator with an x in it. So what can x not equal? Well, from this first one, x cannot equal 0. From here, it cannot equal -1. And from here, it cannot equal 1. And all these are okay because in the top, stuff is the same. So then for the vertical asymptotes, you would say x equals 0, x equals 1, x equals -1. 3 different asymptotes. All right, one more that looks like this. How about this one? F of x equals x plus 2 over x squared plus 6x plus 8. Same routine. Look at the denominator. You need to try and factor it. It actually does factor. It's a trinomial. Factors into x plus 2 times x plus 4. Now, normally I would just go in here and say, all right, look at the denominator. X cannot equal -2. X cannot equal -4. But now here, this is the one special exception, right? Because what have I got in the top? X plus 2. What have I got in the bottom? X plus 2. If that happens, then these sort of negate each other and causes this not to actually be a vertical asymptote. So really, that's not going to be a vertical asymptote. The only thing left is -4. So then you say the vertical asymptote x equals -4, which is 1. Let me do one more. You may have one of these in your homework, just a little bit of a twist on things. Natural log x plus 7. So actually, this is not a rational expression. It's not a fraction. However, though, something different. We've got a natural log function. So what was the concern with these? Why are we so concerned with the denominator? Because in the world of math, you can't ever have 0 in the denominator. Well, in the world of math, there's another one of these kinds of rules. You know what it is? You can never have 0 inside of a log or natural log. It's undefined. So if I've got this here, natural log of x plus 7, I better make sure that x never equals -7. When you have that kind of thing, what that ends up meaning is you have a vertical asymptote of x equals -7. All right, let's move on to horizontal asymptotes. Once again, this should be review. And there are a couple different ways to do this, but I'm just going to do it the way I prefer. And the way I taught. Let's just do some of these. I don't need to teach it, hopefully, because this is going to be review. The whole idea is we're going to cancel in the top and the bottom everything but the leading terms. The leading term in the top is the term with the variable with the largest exponent. In the same way in the bottom. Well, these are pretty simple problems. There's only one term in the top. 8x is the leading term because there's no variable here, so we should have ignored that. So you reduce down to leading terms, and then you cancel and reduce. So I got an x in the top, x in the bottom. X's cancel. 6/8 get reduced to 3/4. The only time we have f of x, if we want to, we can think of y. Y and f of x are the same. So basically, y equals 3/4 is the horizontal asymptote. So if I were to graph that, 1's here, 3/4 is maybe here. Have your graph. How about this one? (4x over x squared minus 3x). Reduced down to leading terms. So on the top, there's only one term. In the bottom, x squared minus 3x, the 3x sort of goes away. Once again, if you want to know the theory behind all this, you can watch the video lecture. 4x over x squared, I can cancel an x on the top and the bottom. So we're saying the function equals approximately 4 over x. Now, as x gets large, maybe you can imagine even as x goes to infinity, what is this function going to be equal to? Or as x goes to negative infinity? Well, either way, it's got to be 0. So horizontal asymptote is basically right on top of the x-axis. So it's interesting, you can see a trend with the first example. You notice the leading term, x and x, they were the same exponents top and bottom. Turns out the horizontal asymptote is just the ratio of these coefficients. Since the variables cancel out, the ratio of the coefficients is 3/4. So there's a case where the leading terms have the same exponent. What happened down here? The leading term in the bottom is larger than the top. So by the time you cancel, you're left with the variable in the bottom. And as that variable gets very, very large, the expression or the function equals 0. So you have a 0 or an asymptote. Just to emphasize it, let me do one that's a little messy, but even though it looks messy, it's pretty simple. 6x to the 4th plus 4x squared minus 7 over 2x to the 5th minus x plus 3. All right, rational expression, try to figure out the horizontal asymptote. Reduce top and bottom to leading terms, cancel, see what happens. X to the 4th is a leading term. I can ignore this on the bottom. X to the 5th is a leading term, ignore this. So I'm going to say this is approximately 6x to the 4th over 2x to the 5th. Now, 4x is canceled on the top and the bottom, and 6 over 2 is 3. So it's like 3 over x. Now to see what the horizontal asymptote is, you ask what happens when the variable x gets very, very large. If you put 1,000,000 in for x or 1,000,000,000 or whatever, what's going to happen? I can't even fit it in. And approximately equals 0. So it's just like this one. This one was not as messy because there weren't as many terms, but the leading term of the top was less than the leading term of the bottom. Same thing here. When that's the case, the horizontal asymptote is always 0. Now there's one type left. And actually, we're going to look at it in the course of actually working out sort of a full problem. So let's just, by full problem, I mean, we're going to now look at all the calculus stuff along with all the algebra stuff. So here, is a problem we're going to look at. X squared minus 9 over x plus 1. Doesn't really look very complicated, doesn't look very messy. So here's a problem where we're going to do all those things I spoke of earlier. We're going to figure out asymptotes, we're going to figure out intercepts, and then we're going to use calculus to determine maximums and minimums and regions of increase and decrease. That's crazy stuff. Usually the progression is, actually most of the time, a lot of people start with intercepts. So for the x-intercept, once again, this is review. What you do is f of x, we can also think of as y. For the x-intercept, you set y equal to 0 and solve for x. I multiply both sides by x plus 1, end up with 0 equals square minus 9. If I solve this, I get two solutions. X equals plus or minus 3. So therefore, if I be very clear about it, I have two x-intercepts, 3 x-intercepts square across this x-axis, 3, 0, and negative 3, 0. So if I'm going to create a graph here as I learn things, I'm going to include them. Three, 0, negative 3, 0. Now for y-intercept, to the opposite, you set x equal to 0 and solve for y. So 0 squared minus 9 over 0 plus 1. So 0 minus 5 of 1 y-intercept. So I plotted some points. So each of my graphs that go through those points. Intercepts. How about asymptotes? How about let's do vertical asymptotes first. So if you look at the denominator and decide what value of x would cause the denominator to be 0. In other words, x cannot be 1. So x equals 1 looks like vertical asymptote. I check the numerator, it's okay. So vertical asymptote, go to x equals 1. Go and draw on my vertical asymptote. All right, pretty straightforward. Now let's see about horizontal asymptote. Now, actually, let me just explain to you what's going to happen because I don't really do very much math. Because what happens is, if I reduce the leading terms, you can see I'd end up with, wow, let's just do it. Sorry, I could explain it, but when I reduce the leading terms, so the 9 gets eliminated, 1 gets eliminated. I'm left with x squared over x. And when I cancel, I'm left with x. So it turns out x is always going up. I mean, the function is always increasing as x is going up. So there really isn't a horizontal asymptote because it just keeps growing or growing. It's not leveling off. However, in this case, especially in the special case where if the numerator in the top is just one more than the numerator at the bottom, then we can have this thing called the oblique asymptote. Once again, I showed an example in class. The oblique asymptote is where you have an asymptote, but sort of a slanted or diagonal line. So based upon that, this function here is going to have an oblique asymptote. How we determine what it is? Well, in this case, the oblique asymptote, first of all, what we're going to be working with, it's a straight line, which means typically equation of a straight line is in slope-intercept form. So for this oblique asymptote, we probably want the equation looks something like this. So I just have to figure out what it is. Now here's what's interesting. Let me write it again. Let's write y equals x squared minus 9. Here's how I do it. Seems crazy, but it's like old-fashioned division. What does that mean? Anytime you had a fraction and you want to divide, we learned a long time ago, you put the top and actually, because there's a term missing, because it goes from x squared to the number, you skip the x to the first. I'm going to go and enter it. I'm going to make it 0x. So it's still 0, but the variable is still sort of there. And then minus 9. So this is what's in the top. I'm going to divide it by what's in the bottom. So there's what you've got. Now by old-fashioned division, hopefully you've done this kind of thing. I say what? Then multiply by x to get x squared. Multiply by x. So x times x is x squared. X times 1 is x. So be careful, because actually what you do now, remember when you do long division, and you subtract the new answer from what was here previously. So this is 0. And this minus carries inside here. So it's really 0 minus x. Then like in division, you bring down the next term. So you have negative x minus 9. So what do I do here? Well, now since there's no x's left, we're pretty much I'm sorry, I misspoke. We got a negative x here, negative 1x. So what times x equals negative x? Obviously negative 1, sorry about that. So negative 1 times x is negative x. Negative 1 times 1 is negative 1. Now you subtract all of that. These cancel out. You get negative 1, negative 9 plus 1. Now, if you can believe it, this right here, I could rewrite it as x minus 1 minus 8 over x plus 1. I mean, So what you do is you take whatever's in the top here, and that goes here. And this is called the remainder. The remainder goes over. And this becomes my denominator. Now, actually, to get a oblique asymptote, what you want to do is asymptotes. Idea is you're looking at your function or your graphs as the values of x get large. As you get way out, way far away. So we're looking at x ends up being big numbers, right? So what happens if I stick in a big number for x here? I'm going to have 8 over a huge number, which once again pretty much goes away, gets so small. So what you're really left with for this asymptote is y equals x minus 1. That is in this form. This is in the form of a straight line. In fact, I can plot it real quick. I guess I could do it up here, right? Y equals x minus 1. Y equals x minus 1. This is going to be a line. Now I'm going to graph this as a straight line. Once again, no time to review. The y-intercept is -1. The slope is 1. So you go 1 up, 1 over. And there's your oblique asymptote. So this one is the equation. This one is the equation y equals x minus 1. And now if you want to actually do the graph, the last step is you sort of got to fill in. Now I've got some points here. So I know that my graph has to be over here somewhere. And I got a point here. But the tricky thing is you have no idea. I mean, if you do this long enough, you sort of start to see a trend. But to be honest, you don't always have any idea what it looks like. So what do? Well, you sort of go old school. What I mean by that? That means you sort of, when all else fails with graphing, you've done all the tricks and you've tried to figure all the stuff out. You can just do the old-fashioned data table. Now, there's my equation. And you start picking some numbers. Sometimes they're messy, sometimes they're not. For instance, if I pick 0, well, actually, I've already done 0 because that's like my y-intercept. How about let's just pick 1, number 1. You plug in 1 in for x at the top and the bottom. So if you plug in for x, you get -8 plus 2, right? Because I put 1 squared minus 9 over 1 plus 1. This is -8 over 2. So I can go here. When x is 1, I can go did I draw the wrong? Wow. Very, very bad mistake. It can happen to anybody. You know what my asymptote should be? X equals -1. See, when I was in this problem, I discovered it. I hate doing that, especially on these videos, because people are probably screaming like, "What you doing?" And maybe you think you're wrong when you're not wrong. So sorry about that. I eventually found it, which is good. And this happens in real life. It can happen to you, it happens to me, it happens to all of us. But it messes up my graph. Anyways, I did find it eventually. Because 1 is -4. Excuse my phone ringing. Actually, I'm going to recreate this graph because it's already going to be sort of messy. It's just going to get really ugly. So let me sort of start again. So here's this. All right. It shows you these math lectures are like real time. Doing them on the fly. Looks like I'm getting ink all over myself. Oh well. 1, 2. So I have a vertical asymptote at x equals -1. I have a oblique asymptote that goes through here and here. I had some intercepts at -3 and 3. And also intercept at -5. Now, let's go do some data points. Sometimes to actually figure out what a graph rate looks like, you got to go plot some points. So when x is 1, y is -4. 1, 2, 3, 4. How about when x is 2? Oh, here's my equation. F of x or y equals I plug in 2. 2 squared is 4. 4 minus 9 is -5/3, which is the same thing as -1 2/3. So when it's 2, -1 2/3 might be now, this graph isn't perfect, but I think what's going to look like when I see these points here, I mean, they're not, I think it's going to end up being something like this. Now let's see what happens over here. Well, I can say I got 1 point here. Let's see what happens when x is -2. When x is -2, you put a -2 in here and you get 4 minus 9, which is -5 over -1, should be 5. One, 2, 3, 4, 5. Oh, I plotted it wrong. That's a 3 because I was saying, why is it the same as this one? All right, it's better. Let's do one more point. Let's go like to -4 and see what happens. Like a -4 for x. 16 minus 9 is 7. 7 over -3, which is -2 and 1/3. 1, 2. And I think if we did more and more points, I'm saying you start doing this enough, and you start seeing these trends. So there's the graph. Now for the calculus part, one of the first things they ask for are what are the maxes and mins? Well, if you look at this graph, what would your answer be? Your relative maxes and mins are things like this, right? We don't actually have any relative maxes or mins, so there aren't any. Now, what they do ask are regions or intervals where the function increases or decreases. What does that mean? Left or right, right? You start at the left part and as you move to the right, what's going on? So it starts here at negative infinity, and it's increasing, 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 increasing up until it hits this asymptote, which is -1. So increasing region, negative infinity to -1. This is an interval. So you jump over the asymptote and you go down here, and as you keep moving to the right, it keeps increasing. So there are two regions of increase, negative infinity to -1, and -1 to infinity. Turns out this whole graph is actually increasing. So there's no regions where it's decreasing. How about the point of inflection? Point of inflection like this is where you're looking at concavity. So this is concave down and then concave up. The point at which concavity flips is called the point of inflection. And if we look up here, what do we have for concavity? This is like concave up. It's always like a bowl. I jump down here and I move to the right, and this part's concave down, but they're not connected, so it's two separate parts. So this half of the graph is concave up, this half is concave down, but there's no point of inflection because it doesn't really, if these were continuous in changes, that's one thing, but when you got this break in between, there's actually no points of inflection. So you would say for concave up, x would be negative infinity to -1, and then concave down, x equals -1 to infinity. Sorry, that's what I was writing. So concave up, -1, or negative infinity to -1, and then concave down, -1 to infinity. So here's actually a problem where we didn't have to really do any calculus per se. We just had to understand what things mean. There will be problems where you will have to do calculus. You will have to take the first derivative, set the first derivative equal to 0, find your maxes and mins. And I may come back and do one of those, but let me stop for now. And maybe I'll do one more problem that's a little more involved.